So, hello everyone. Welcome to this OpenFOAM 16 workshop. Today I'm going to present to you an introduction to cloud-based simulation with SimScale. So let's jump straight into it, and the focus will be electronics cooling and the SimScale API. So a little bit about myself. So I'm a product marketing engineer at SimScale. I specialized in computational mechanics as well as fluid mechanics, studied at KIT. And of course, if you want to connect after the session, feel free to connect with me on LinkedIn or on YouTube. Quickly about the agenda for today. So we'll have an introduction to SimScale, what SimScale actually is about, then a little bit about the company. Then we'll start talking about simulation, why we need simulation and when do we invoke a simulation process. Point number 4 talks about the traditional design process versus SimScale. It's not so much about versus SimScale, but more how you can use SimScale to accelerate your design process. Point number 5 deals with CHD applications and how you can use SimScale for those applications in particular. Point number 6 API. At the end, I'll give some closing remarks and we will close the session with a relaxed Q&A session. So a little bit about SimScale. So SimScale was founded in 2012 in Munich. Our headquarters is also located in Munich, but we have also had offices in Boston as well as in New York. We are roughly about 90 plus employees and distributed across 8 different time zones. We have now over 160,000 users worldwide, and with over 300,000 simulation projects, we are the go-to platform for simulation. And what do we actually do? Well, SimScale created the world's first cloud-based engineering simulation platform. And what you can do is you can simulate CFD, FEA, and thermodynamics applications inside of your browser. So the only thing you need is an account and at least an internet connection. So the problems of traditional simulation are as follows. Usually you often have very high fixed costs and you need special hardware requirements. For example, when you think back of when you studied engineering, for example, and you had a specific FEA or CFD case to run, sometimes you had to run on your machine and didn't have any workstations, which was kind of a tedious process. What comes with that is also like the very tedious installation. Sometimes you need to have a team to maintain the software package or this workstation. Unfortunately, this traditional simulation packages are all often built for specialists. And with that comes also a bit of training that needs to be done in order to master the simulation software. And of course, your engineering experience and knowledge. Also, the computation which is used for these simulation purposes or simulation setups often takes days or weeks. So to make this whole thing interactive, I also included some polls for you. And the first question would be, if you're already using cloud-based simulation software, and I'm starting the poll right now, and you could already vote. I'll give you 10 to 15 seconds to vote. Okay, looks good so far. Okay, 3 more seconds. Okay, as you could see, it's like 50-50. So it's, first of all, for those of you who did not use cloud-based simulation technology before or software, I think it's a good thing that you're here now and learn more about cloud-based simulation technology. So let's move on. So first of all, why should you even care about simulation in the first place? I think a lot of you know what simulation actually is about, but let me kind of motivate why you should use simulation. So we kind of have this graph about the product development process or product development processes in general. And the thing is that you have several stages of the product development process. So we first of all have the idea process, then you go over to a concept phase, then the realization phase, and then the validation step. And the thing is that the more you go towards an end product, the freedom of doing changes on your product significantly decreases. So what you can do in order to simulate different scenarios is to invoke or use simulation technology in the first stages of your design process. We often call that in CFD, for example, front loading. So what that means is we use IT solutions, in this case SimScale, to iterate through different design steps and then decide for ourselves what the best design could be and then move forward. Also, what you have to take into account that the cost drastically increases. That means the more we move forward in the validation step, the more expensive it becomes to make changes on our product. So in order to not only fasten the time to market transition or accelerate the time to market transition, we also have to think about we waste basically more time by doing more prototypes. But I'll talk about prototypes in a few seconds. The next part already is here. So the usage of simulation. How do you use simulation in your company? Don't you use it at all? Do you outsource simulation? Do you have a dedicated simulation department? Or do you have simulation access for your designers? Let me start this right now. I think it's even a multiple choice question. So you could choose several options. A few votes are coming in. Give 5 more seconds to vote. Perfect. So what you can see is that 100% actually have a simulation department of those who voted. So that's very interesting. And I'll show you definitely why you would or why you could use SimScale to accelerate your design process. Thank you so much for participating. So what are the benefits of using simulation? Well, first of all, you have an optimized design. That means you don't have to have a prototype, but you can use simulation in general to optimize your design and run several iterations in your with the software. And as I already mentioned, you have fewer physical prototypes. I'm not saying that simulation makes prototyping redundant, but kind of you have less prototypes, which saves you money and of course time. Point number 3 is already what I said. You have significant cost reduction by using simulation, and you can investigate what if scenarios. And I'll show you in the case study how you could actually do that. And as already motivated by the graph, by the plot I've shown you, you have a faster time to market transition, which sets you apart from your competitors. This we already covered. And now the benefits of using SimScale. So with SimScale, you have the benefit of having no upfront investment. That means you create an account, you have a special number of core hours that you can use, and you can basically already start simulating. Also, a very nice aspect of SimScale is that you have no installation or maintenance requirements. That means you only need a browser, as I mentioned earlier on, and a decent internet connection, and then you can start simulating. It's pretty simple. Of course, it's a very easy setup. And what I really like is the seamless collaboration tool. That means if you use SimScale for your company, for example, and you have a project which you set on private, which you could do if you have a special account, then you could share it with colleagues. They could have a look at it, copy the project, make some adaptations, and you could have several versions that you could share with each other and work on one project, which is really exciting. And of course, we have world-class support. That means if you have any issues, any problems with the simulation, my colleagues are happy to help you out in case you run into any problems. And also by using HPC systems, you can take computation time from weeks to literally minutes. So there's a simple 3-step process how you use SimScale. So first of all, you upload a CAD model. It doesn't have to be one CAD model. It can be like tens and even hundreds of CAD models in one project. And the second step, of course, we have the processing step by defining the boundary conditions, abbreviated by BC here. And then the last step, of course, you investigate your simulation by post-processing the results inside of your browser. That's very important. So you don't need to install ParaView, for example, or TechPlot, but you have the post-processor inside of your browser. So quickly about the traditional design process. So in the beginning, you have the design, then you go over to the physical prototyping, which is kind of an iterative process. So you have a prototype, then you make some changes, go back to the beginning and do it as so long until you're satisfied, and then you would eventually go into production. By front-loading your design process with SimScale, you can basically run tens and hundreds of simulations in parallel without feeling any lag on your machine, because it's basically sent to the server, calculated there, and the results will be sent back to your machine or to your account. And you can save money as well as time, which is indicated by this great animation here. So kind of have this in tabular format. So what you can see by physical testing, we often have only a few designs. The turnaround time is often days, if not weeks, and we have hundreds and even thousands of dollars for each iteration. If you use classical traditional simulation tools, so in-house simulation, you could run several tens of simulations in serial. It takes hours for each iteration, and the cost, well, it depends on which software package you use. And then in the last column, you could see SimScale with basically unlimited design iterations running in parallel. And the turnaround times are hours for all iterations, not for each iteration, but for all. And the cost is between tens and hundreds of euros. So very, very cheap and accessible as well as affordable. So I want to know from you now, what is the most important criterion for a simulation tool for you? Is it the pricing? Is it the accessibility? Is it accuracy of the solver, or the minimal effort for pre-processing? What I mean by that is CAD work. Would be very interesting to see how you vote to get an idea of what's most important for you. So the poll is live now. Very interesting. We're in for 5 more seconds. Some more votes are coming in. Very nice. So let me share the results. So what you can see, a lot of people are interested in pricing and also minimal effort. I can tell you for all the points that SimScale is very, very confident that you, first of all, have a nice pricing. So you would have a tailor-made pricing model for your company or for your project that you're working on. Of course, obviously, it's very accessible. The solvers are all validated at SimScale. And the nice thing is about CAD work that we have recently launched CAD mode at SimScale. So what you could do is you can upload your CAD model and see if you have any issues with your CAD. You could go into so-called CAD mode and optimize your CAD inside of the browser, which is really, really exciting. So now about CFD thermal management. What applications could you simulate in the special field of thermal analysis? So for example, applications, what you can see here is an electric vehicle battery pack, which we have simulated using SimScale. So some applications, just to give you a few examples, then we move on, is you could simulate natural and forced convection. You could cool your applications with air or liquid cooling. You can even use fan modeling. You could have anisotropic materials, for example, if you have a PCB. What's also very interesting is you could have thin layer resistance and model that, and also thermal interface materials. For example, if you have a processor, and then you would use a thermal interface material. That's all possible on the SimScale platform. And last but not least, you could also simulate power networks. Some applications before we jump to this case study. What you can see in the first row is basically the enclosure cooling, which we'll have a look at in a few seconds. What we also did is here a nice simulation of a GPU enclosure, which you could simulate. Then we have from our customer OnLogic an IoT edge device enclosure, which they simulated and very efficiently simulated. And the second row shows you the liquid cooled applications, for example, for power electronics or IGBT mounting plate. A few more before we move on, you could also see LED thermal management. So lighting applications also are easily applicable if you want to simulate them on our platform. Enclosure cooling, for example, data center cooling to save energy and kind of want to investigate how the heat distributes across a room. We have medical equipment cooling and also drone electronics cooling applications. So the possibilities are basically endless. So before we move on, I want to know from you now, from the participants, what's your level of experience with simulation? Are you a professional user? Do you have an academic background, or are you a hobbyist? Would be interesting to know, because it's kind of nice to know on which level you are. Very interesting. A lot of academic people here as well, but also professionals. Give you 5 more seconds. Okay. So what you can see is there's most of them are academic. If you have an academic background, but we also have professionals here, which is very exciting to see. So let's move on to our design study. I want to quickly walk through it and just let you know that you could basically show you the possibilities of SimScale, what you can do with it. Of course, this is not the only application, but just to give you an idea of what you could potentially do. So we have this nice board right here, and we have some data about this. We have small chips with a specific power, or you have the CPU, you have the transformer, some smaller capacitors, and then you could assign the boundary conditions to these components and kind of already start simulating. The cooling strategy that we use in this case is so-called forced convection. So we have fans, which you could see right in the front of this this right here. What you could do is you do not even have to explicitly model the fans, which is really, really nice. You could use something like fan curves and use that to kind of model fan behavior. And of course, it's kind of blurred out, but what you could also use is natural convection modeling. You could have like a phase change approach, or could have a liquid cooling approach, but we want to focus on the forced convection aspect. Right, and as you can see, the ventilator inlet gives us, or is 20 degrees Celsius, and you could see here on the upper side, we have the outlet opening, which is also defined in our simulation setup. Right, some more design specifications. It's not too important, but just in case you wanted to know how it was performed. And of course, if you want to simulate your own or copy even this project, you can easily find it in the public projects library. If you want to play around with it, feel free to write me a message and I'm happy to share the project with you. Some design parameters that we could vary is, for example, the heatsink design. So do we have like fins? Do we have like maybe another design that we want to use? We could, of course, change the fan opening, for example, how big it is, and see if we kind of have some recirculation zones depending on the size and the speed of the inlet. But of course, you can easily replace the components and see how the temperature distribution and also velocity distribution will change. And also, in terms of energy consumption, investigate the pressure drop, for example. So here would be the results for the simulation. What you can see is that in the first case, on the left-hand side, we have the temperature in Kelvin. And on the right-hand side, we have the velocity in meters per second. And as you can see right here, here was the inlet. And on the upper side, you could see the outlet. And what you can also do now is to kind of see if there's any change in the flow behavior or temperature behavior. What we do now is we change the heatsink design. So we go from a fin heatsink to a pin-fin heatsink and see how this would change our design or temperature distribution. So this is what the post-processing would look like. It's the same temperature scale. So what you could immediately see is, for example, that this transformator here is a bit cooler, what you can see, just by giving you like a rough estimation. And the temperature of the heatsink is also way cooler. Having a top view on our component or investigation, what you can see here, how also the temperature behavior changed. What you can see is that these components here, the chips are also a bit cooler now, the transformator, as I already mentioned, and of course the heatsink is way cooler as compared to the other heatsink design. To have a look at the flow field, what you can immediately see is also how the flow field changes, if there's kind of any blockage effects or maybe some recirculations. It cannot be investigated that easily if there are any recirculations. So what you usually do is impose some kind of vector field and see if there's kind of a like turning arrows or like to kind of investigate if there's like a recirculation zone. If that would be the case, you could have the option to redesign your component or replace the components and easily run another iteration in parallel. So what we achieved with the heatsink design change is basically a reduction in the temperature of the CPU temperature of 16%, which is quite significant. So this is how we changed the system performance. And it didn't even take hours to do this. It literally takes minutes. So what you could even do is you could start this simulation run here on the top. You could start the second one in parallel and you would feel absolutely no lag or like decrease in performance on your machine because it's basically sent to AWS servers, calculated there by high performance computing clusters, and then sent back to you, to your machine. So quickly having a look at design study or optimization number 2, we varied the design by having a baseline design with an inlet of 15 meters per second. Then we go 10 meters per second and then 20 meters per second, and then basically see how the temperature behaves. Right. So what you can see and what you would also expect is that with the slowest velocity, you would have the highest temperature for the components, because it's a bit intuitive. You kind of can assume it, but of course you would like to verify your intuition with the simulation and not rely too much on your intuition. And kind of the lowest temperature, and please note that this is the same temperature scale for 20 meters per second. We have the lowest temperature. Also a top view here again to kind of see how the different inlet flows kind of change the temperature of the devices. And what we could achieve with a different inlet flow is basically a temperature gain, or like a decrease of the temperature by 5%, which doesn't sound too bad, but you have to imagine that even that little of a change in the performance or the system reliability could have significant long-term benefits. Right. And of course, as I already mentioned, these 3 runs were run in parallel, so you don't even have to wait that one simulation is finished, but you could even run like from 5 to, I don't know, maybe 30 meters per second, all in parallel, and kind of get your results and check them out on the fly. I want to quickly talk about the SimScale API. It's not too much important. It shouldn't be like the focus of this talk, but in case you have a machine learning application or like optimization case studies, maybe use Dakota or whatnot, you could use our SimScale API. So we have Python and C# SDKs, which you could use to to give you like a holistic overview of what applications we have. For example, what you could use it with is like ParaView. We have a Python SDK, as mentioned, C#. You could use it for parametric sweeps, shape optimization, for example, and we offer a variety of state-of-the-art technology. So you could, for example, we had a nice application case where a valve was optimized. So we had a shape optimization of a valve, which one partner used the API for, and we had several other applications. I'll go into a little bit into detail in a few seconds, but if you have any applications would like to test out the API, feel free to reach out to us. So this is just an API code example that I want to show. It's very, very easy to use. As already mentioned, we have C# and Python SDKs available on GitHub. If you want to have a look at them, feel free to reach out to us, and I'm happy to share the GitHub repo with you. And you could basically run simulation setups and have result processing in a few hundred lines of code, which is very, very exciting. But we also have pre-made templates that you could use. Right. How the roadmap would look like. So for the Python SDK, you could basically just scan this QR code. We have some capabilities for our LBM solver, so our lattice Boltzmann solver, which you could use the API for. We also had a nice wind tunnel app, which was launched by Thornton Tomasetti, one of our partners. Also, we have an integration with Gnosis and their software Optimus. And we have a webinar on June 29th, which I'll announce also in a few seconds, which you could participate in and see what the capabilities of the API are. And also on the roadmap, what you could see is some CHT capabilities for the OpenFOAM solver, some post-processing capabilities, and also moving towards FEA enablement for the API. So please, if you have any questions, any thoughts, or want to use the API, or have any questions, reach out to api@simscale.com. So as already mentioned, June 29th is the Tesla valve design optimization case study with Gnosis. So I would like to invite you there and have a look at how they used their tool Optimus to optimize this Tesla valve design using the SimScale API. Where you can find this basically on the webinars page of SimScale. We also have some on-demand content for you. So if you're interested in CFD, how to use the lattice Boltzmann solver for example, pedestrian wind comfort, or use SimScale for CHT applications for electronics cooling devices, whether it's lighting, whether it's batteries for electric vehicles, or if it's enclosure cooling, then feel free to check it out. If you have a topic which is not listed on the webinars page and would like to learn more about your own case, feel free to reach out and we're happy to help you out. And as mentioned earlier on, the only thing you need to do to get started with SimScale is to create a free account under simscale.com/signup. Get started. You have 3,000 core hours that you can start with, copy some nice simulation projects from the public projects library, and basically start simulating and start playing with some simulations. That is all from my side, ladies and gentlemen. If you have any questions right now, I'm happy to answer them. So feel free to put everything in the Q&A section. I'm happy to check it out. Of course, if you don't have any questions now, feel free to reach out to me via LinkedIn or email, and I'm happy to support you. I think I give you like 5 minutes, maybe 3 to 5 minutes to post your question if you have any. If you have a question about a specific slide also, we could tackle that question as well. Seems like there are no questions. So I'm not sure if that's a good or a bad sign. So that's up for you to decide. And please don't hesitate to get in touch with me if you have any questions. Even if it's not about electronic schooling now, but maybe you're interested in pedestrian wind comfort, want to give the Lattice-Boltzmann solver a spin for your professional application. Ravi Khan, thank you so much for the question. He asked how is SimScale associated with OpenFOAM? So for CFD, OpenFOAM is kind of running in the background, but you have to pay attention. It's not OpenFOAM per se in the sense of that it's like the 101 copied. Simply the backend is just OpenFOAM, how you can download it. So our developers have made plenty of changes on that OpenFOAM version. So it's kind of OpenFOAM, but also not OpenFOAM, if you get what I mean. So it was drastically changed also in terms of how the code performs. The CHT solver, for example, was also changed drastically. So we have a CHT V2 solver, which is way, way more performant and way faster than it was before. There's also another question, can we run our own solver on SimScale? That's not possible yet. So the issue with scripting in general, if that's what your question aims towards, is that there are also security issues involved. But I have some applications. So for example, if let's say you have a machine learning application, you want to run Keras code with the API, we have some projects doing that already. So if you have any ideas on how to use the API for your own project, feel free to reach out. Maybe let me just jump back to the API slide. You could maybe check out the QR code or write an email to my colleague Anatol, who is like the responsible guy for the API at api@simscale.com. Was kind of a fast presentation, but now you have also time to listen to other interesting presentations which run in parallel. Any more questions? Okay. Doesn't seem like there are any more questions, ladies and gentlemen, so I would close the session right now. And as I already mentioned, if you want to reach out, please do so. I'm happy to chat with you if you have any applications, and then we can certainly find a solution on how to make your case successful. So with that being said, thank you so much for attending and hope to see you around. And also feel free to maybe contact me via this chat functionality here on the platform. And see you soon. I wish you an awesome day, an awesome weekend, and see you soon.